I'm going to start speaking.
Yes.
Okay, so thank you for coming to the Fall 2019 Atmospheric Sciences Invited Speaker event. Our speaker today is Dr. Christine Wiedinmyer, who is currently the Associate Director for Science at CIRES. That's the Cooperative Institute for Research Environmental Sciences, or basically the equivalent of our CIMAS, but at the University of Colorado in Boulder. And Christine told me today that it has 900 employees. So you thought we were special. Christine
We're all special.
She grew up near Philadelphia, and she got a Bachelor's of Science in Chemical Engineering from Tulane University, and then a Master's and a PhD in Chemical Engineering at the University of Texas Austin. She was a scientist at NCAR for 16 years, 2001 to 2017. And mysteriously, she agreed to step away from that position and take on this role as Associate Director for Science at CIRES, which I'm sure is great for CIRES. She's an expert with over 100 papers, which are related to trace gases and particles in the atmosphere. And so we're very lucky she came down to give a talk for us. And it looks like we're getting very close here.
We're coming, but I can skip over a couple of things to get started if you want.
Anyway.
So thank you all for coming, and thank you so much for having me. I was telling everyone I left yesterday in a blizzard, and I think the high today is 15 degrees, and so this has been awesome. And I'm so happy. My kids went to school late, and CU closed yesterday and opened late today, so it's great to be here. Look at that. And today I'm going to talk. Let's do this. I'm going to talk about a lot of projects that I've been on. So I'd rather give you a breadth of what I'm interested in. So if anyone is interested in any one thing, please come and talk to me or follow up with an email. And if anyone wants to talk more in depth, stop me in the middle of the talk and I will explain further. Basically, I do nothing in a vacuum. I have a ton of really amazing collaborators, and I have to at least acknowledge some here who have helped me with a lot of the work that I'm going to present today, including Bobby Okelson, Mike Hannigan, Kelly Barsanti, Anne-Marie Carlton, Louisa Emmons, and others at NCAR, my colleagues there, Elena McDonald-Buller and Yo Kimura from the University of Texas, Amber Sodia, Jesse McCarthy, Dom Spracklin, and his grad student Laura Kilty, and then Khalid Held. So again, I'll point them out as I go through, but I really want to acknowledge again that I have amazing collaborators who really are the reason why work gets done. So basically, my whole career has been spent on trying to understand emissions of greenhouse gases, emissions of trace reactive gases, emissions of particles, and then how they impact air quality and climate. Because without accurate assessments of emission inventories, you cannot figure out how to best mitigate our air pollution problems. We can't understand what's going on in climate change. So emissions and understanding what's going up into the air is extremely important. And so the beginning of my career, I spent looking at biogenic emissions of volatile organic compounds, or you'll hear me say VOCs. These are compounds. You're walking through a pine forest, you smell those pine forest smells. Those are all organic compounds that on their own are fine, not harmful, but when they mix with anthropogenic or man-made pollutants, they can create issues. And in order to understand what's going on a regional and global effort or scales, you really have to know what's coming from the trees. And then I moved towards disturbed vegetation. So trees on their own emit these VOCs, but then when they're burning, they emit a whole other suite of compounds and particles. And then from there, I looked at, okay, biomass burning outside, but what happens when you bring it inside, and start looking at residential heating and cooking. And so today, I'm just going to focus on the fire components, and I really want to acknowledge all my different funding sources for the work that I'm going to present today. And again, I'll just focus on these two. So basically, when I'm talking about outdoor fires and outdoor biomass burning, I'm talking about anything from wildfires, prescribed burning, agricultural burning, land clearing burning. And this is a map showing satellite fire activity around the globe for a year. And it's rather old, but it's still relevant today. And basically, the points I want you to take away from here is anywhere you have vegetation on the ground, you have some kind of fire activity. And you can see that the biggest activities are in the southern hemisphere, Africa, South America, Southeast Asia. And then if you look at, let's see if I can get this to work. This is just that satellite activity shown by month. So you can see that, of course, the fire activity doesn't occur all the time everywhere. It varies depending on what time of year it is. And so this just gives you a sense about the fire activity, where and when it happens over multiple years. And again, these are all just detections of fires from space. So yeah, I think it's fascinating. And it's interesting, I live in the western United States. You think that the western forest fires that we're exposed to all the time are so big and impactful, but you know, on a global scale, actually fires in the West are pretty small. So again, I look at the emissions from those fires. And I'm going to show a couple of pictures here, and I just want to point out, these are photographs not from me, but by a National Geographic photographer who was on a journalistic fellowship at CU, and somehow she found our group and went in the field with us and shared all of her amazing pictures. So now I have really nice photos to show during some of my presentations. And when we talk about smoke or fire emissions, we're not talking about one thing. You have particles that are emitted from fires. You have different types of carbon. Black carbon, that's the black smoke that you see, mostly from flaming combustion. And then you can have this organic carbon, the white carbon. It comes from smoldering. You often see the white particles. And then we also have a whole lot of other different compounds. Oh, gosh, this is fun. Inorganic components of the particles that are also make up those particles that are emitted. And then you have a whole bunch of different trace gases. So these are reactive gases. You'll see me say NMOC. This is non-methane organic compounds or volatile organic compounds. Sulfur dioxide, oxides of nitrogen that are formed from combustion processes. You even see ammonia coming out of fire plumes, and it can be detected from space. So I'm interested in all of these different things. And so a long time ago, someone came to me and said, oh, you do biogenic emissions. We're waiting on this really good group to do fire emissions inventory for us, but they're taking so long. Could you do something quick and dirty while we're waiting? And that resulted in my entire career, it seems like, but that resulted in a model of fire emissions from North America. So I presented this and gave this to the EPA and other people to help them determine how much fires were impacting air quality. And my whole goal was to provide a product that was quick and easy, but could be used really readily by anyone. And then that led to the fire inventory from NCAR or FIN. That became a global model that predicts fire emissions on about a resolution of about 1 kilometer, daily emissions. I wanted to make this available for multiple applications, not just for modeling in the past, but also for forecasting applications. And I wanted to predict emissions of anything that people would be caring about. So we have greenhouse gases, we have these reactive gases, we have particles. I even have things like mercury. And just a side note, so the model is named FIN. I worked for a long time with Alex Gunther, who is an expert in biogenic emissions, and his model is called MEGAN, or the Model of Emissions of Gases and Aerosols from Nature. So his daughter's name was Megan. So when it came time for me to name my model, we had to come up with either Maggie or Finn, because those are my two kids' names. So Finn won out, and now Finn thinks he's famous. So basically, emissions can be calculated as a function of an emission factor, so the mass of pollutant that's emitted per mass of biomass burned. This can be dependent on the vegetation, so the vegetation outside, if we burn that, might produce different emissions and different chemicals than if we burned a pine forest. It can also differ based on the fire stage or intensity. Like you saw, that black carbon might be emitted by flaming combustion, whereas white carbon is from smoldering. It's also dependent on that biomass burned, again, like the type of vegetation and the amount. And then also there's new models that predict emissions based on this FRP, or fire radiative power. It's a parameter that can be observed from space, and it's kind of like the energy being radiated from the ground, and they can back calculate that to say, okay, that is equivalent to the amount of biomass burned, and then they can multiply that by emission factor and get emissions burned. I use a variety of different satellite products. For example, this little square, so the red marks are so these are the detections from space that tell me when and where a fire is occurring. And then I overlay that on different maps of vegetation type as well as density. So in my default model, we use the MODIS land cover type product as well as the vegetation continuous fields product to help tell me when, where, how much is burned. And then I've been fortunate enough to work with amazing chemists who go either into the lab or they fly airplanes around biomass burning plumes, and they measure different compounds and come up with emission factors. There have been many studies in the last 10, 15 years, and I'm going to talk about some of the challenges from a modeling perspective of how to incorporate all the data that's been collected. But the data we use in the models are from both these lab and aircraft measurements. And one thing, you don't need to know all these chemical compounds, but the whole thing is there's been hundreds of chemical compounds emitted and measured from biomass burning. This is actually from a compilation that we did of emission factors from the published literature in 2011. And this is sorely outdated. In fact, we're trying to have a group of us come together next spring to redo it. But the point here is we have all sorts of different gases. There's not one thing. They all do different things in the atmosphere. Some of them have bad health effects just on their own. And then they can have numerous impacts on air quality and climate. So smoke is not one thing. There's a whole bunch of different compounds that are measured. And big questions are what happens to them and how do we best understand their impacts. So just so you can get an idea of the magnitude and importance of fire emissions just globally, this is just a pie chart showing you the carbon emitted from fossil fuel burning or fossil fuel combustion relative to the fire we predict being emitted from biomass burning. So it's not huge compared to fossil fuels, but it is an important part of the carbon cycle. And again, this is just carbon going up. It's not talking about any of the carbon being reabsorbed after biomass burning happens. If we look at those reactive trace gases that can have impacts on air quality, these are nitrogen oxides, so think of emissions from your tailpipe or power plant. Overall, fires emit relatively little of the overall global NOx budget. But if we look at carbon monoxide, it's nearly half of the global carbon monoxide budget. And carbon monoxide is very important for chemistry. And then we have these non-methane organic carbon compounds. The green piece of the pie, again, is that biogenic emissions piece that I talked about. So the number one compound is isoprene. We also have monoterpenes, a whole lot of others. And then we have a reasonable piece from anthropogenic sources. And then here we have a small piece of the pie from fires. However, this piece was actually made way before we had the ability to measure more and quantify more products. So I actually think this is underestimated by at least a factor of 2 to 3. Recent data have really shown that this piece of the pie is much, much bigger. And then if we look at particles in the air, so this is particulate black carbon, particulate organic carbon, that black and white carbon. And then I also have the pieces of the pie by particle size. So PM2.5 are those fine particles that can get deep in the lungs. They're what we do all of our health regulations about. And then PM10 is more coarse particles that are still important for climate and air quality. And the red piece of the pie is that open biomass burning piece. So you can see that for particles, biomass burning really contributes a significant amount of the particles being emitted to the atmosphere. This is extremely important for climate predictions and understanding climate impacts. The other thing that I want to point out here is that piece of the purple pie is the residential biomass burning. So this is biomass burning, emissions from biomass burning that in households that use fire to cook and to heat their homes. So together, both indoor and outdoor biomass burning contribute to 73% of the direct emissions of black carbon particulate black carbon and 93% of the particulate organic carbon. So it is really, really important. And so, we do a lot to try to understand those emissions, better constrain them, and then look at all their impacts across air quality, weather, and climate, and then even for health. And I'll just hit on each one of these a little bit. So there's some really great papers looking at the contributions of particles from biomass burning and how they impact air quality. And I really, really like this paper because it's scary. So here they looked at the fraction of PM2.5, those fine particles that can get into your lungs that are caused by biomass burning across the western United States every year. And you can see, on average, it's like 20-25%, maybe tops in some areas. But if we look at those days where those PM2.5 actually exceeds the health standard, so they fail the EPA standards and it's unhealthy for people to breathe, you can see that biomass burning contributes 90 to nearly 100% of that PM2.5. That means that in the western United States, when we fail our health standards, it's almost always driven by biomass burning. So this leads to serious questions for air quality managers, for fire managers, for how we deal with our forests across the West, because we do know that our fire seasons are getting longer, they're getting more severe, and they're gonna have bigger impacts moving forward. So we look not only in the US, but across the world, and this is one example from 2015. There was a big El Nino year, and what happens in Southeast Asia, Sumatra, Borneo, is that Indonesia, is that people typically clear their land. A lot of this is driven by oil palm plantation and people changing and converting the forest to agriculture. And what happens is it dries out during El Nino years, people light the fires, and then the fires tend to burn all the peat. There's meters and meters of peat, so organic soil, that can burn. And this happened actually just recently, last month, and this happened in 2015. And you can see here, this is just a satellite image of the same area, and you can see where the fires are in red and that the smoke encompassed the entire area. Became a huge deal. There was all sorts of, actually there's a lot of press about the most recent case, but it caused a lot of people to have health problems across the region. It also caused a lot of political conflicts between Indonesia and some of the other area countries, just because it's happening in Indonesia, but the smoke is impacting Malaysia and Singapore and elsewhere. So it leads to a lot of issues. And these are just pictures of Singapore on a clear day and during that episode. So you can see that was pretty impactful. So one of the things is you can see it from space, but how else can you show the impact of those fires on the air quality throughout the region? So we came up with estimates of where the emissions were, and this is just a map of the emissions, the particles for that time period. And then we put it into a regional air quality model to try to simulate and see if we can best capture and understand what happened in that time period. So you can see here the emissions going off from day to day, and then how far the smoke can travel. And we thought we did a pretty good job. This is with the regional, or the weather research and forecasting model with chemistry. So it's an online chemistry weather forecasting model. And then we can go back and look at measurements from the ground and see how well we do it. Sometimes we did okay, sometimes we didn't. Yes? Yes.
And then what happens in the model?
Oh, yeah, that's a good question.
Okay.
So,
it's too much, but
no, so we put the emissions into, it's one input into this model. We also put all the other anthropogenic emissions, and then it's a weather model. So in this case, we don't have feedbacks. I'll talk about that in just a second. We just take the emissions and we push them around. And in this case, I don't think there's any chemistry going on. I think they're just bulk tracers. So we're not looking at all the other secondary processes or the ozone formation. We're just looking at where the particles get transported to see how well, how good are we doing with the emissions. Obviously, this day we didn't do very good, because the measurements were much lower. So what happened that day? Did we miss the fire detections, or, do we push the plume somewhere else? It helps us evaluate not only the emissions, but also the meteorology in the area.
So this is Wharf Chem, but just pushing around particles.
Yeah, it's not full chemistry. Oh, it could have been full chemistry, but what I'm showing here is just total particles, PM 2.5. Yeah.
One question, like how far from the ground you guys, how you quantify, like, is it like the temperature?
Yeah.
Or the measurements?
So the measurements, these are measurements at the surface, and they're compared directly to the measurement to the model output at the surface. However, and this is a conversation that I had earlier, I mean, there's questions and really big uncertainties as you have the emissions, and then do you put them all in the surface? We know that fires get vertically input into the boundary layer, and sometimes, depending on the magnitude of the fire, it can pop the boundary layer and go higher. So where do you put those emissions into the atmosphere? And I think that's a huge question, and we still don't know. I mean, I think the value of the field campaigns that are going on right now to help us identify where the fire plumes are, where they get transported, will help us better constrain the vertical distribution of the emissions. But I work with a colleague, I'm going to go off a little bit. But I work with a colleague, Maria Val-Martin, who is at Sheffield University, and she's taken the MISER data, and now I think she's working with a newer satellite, and finding all the fire plumes around the globe that the MISER instrument has collected and come up with parameterizations of plume rise based on what that LiDAR or what the MISER instrument has seen, and what type of fire has been burning and how it's been injected. There's other ways to try to figure that out based on the power radiated from the fire. Some models are actually using the same equations that we use to predict the emissions from power plants and how far they're emitted into the air, and using those same Briggs equations on fires based on the power or the heat emitted. But it's a huge, huge, huge uncertainty, I think. Another big uncertainty is the feedbacks. You just asked about like whether it's just a tracer. What's nice about this Wharf Chem model is we can also turn on radiative feedbacks. So we can have the chemistry going, we can have all the trace gases mixing and chemically reacting. And then we can also turn on and say, okay, when there's particles in the air, let them, based on whether they're dark or light, let them scatter light or absorb light. And by including those radiative feedbacks, you can get really different answers. And I think this is really important moving forward. If we're really going to understand the chemistry and climate impacts, we need to include all these radiative feedbacks. Right now, most of our air quality models that are used to understand air quality impacts are just putting in the emissions and letting them go. They're not having that radiative feedback happen. So what we did was we took these big fires in Idaho and we put them into this weather forecast model, and we turned on that radiation feedback. And what we saw was that we got changes in our boundary layer depth when we added that, because of course if you're heating or cooling the atmosphere with particles, you're either going to change the boundary layer depth, and you can also change that surface temperature. If you change the surface temperature, you're going to change the biogenic emissions, which are impacted by surface temperature. So, and this boundary layer height and that surface air temperature. So we saw these changes. And by including those changes, we were seeing up to 60% changes in predicted ozone concentrations. So it's dramatically impacting our predicted chemistry downwind. So again, I really hope that this kind of interactions are included in future air quality modeling. And I'll just talk a little bit about health. I'm fortunate enough to be at CU with Colleen Reed. She's in the geography department there and is an epidemiologist, and she wrote this really nice review. We've seen all sorts of health outcomes, negative health outcomes associated with exposure to biomass burning, from increases to COPD, asthma, respiratory diseases. They've seen cardiovascular outcomes, and then even potential impacts on birth outcomes. And this is an older study, but there's been two more recently that confirm this, that they looked at the fires in Southern California in 2003. And they had a cohort of women who were pregnant before, during, or after the fires. And what they found was that women who were exposed to the biomass burning smoke during their pregnancy had children with statistically lower birth weights. So being exposed to biomass burning is now associated with lower birth weights, which is, I thought, a fascinating result. And I think there's there's going to be a whole lot of other studies going on with all the fires we've had across the West. Faye Johnson and a group put predicted fire emissions and put them into a model and simulated surface PM 2.5 concentrations, and then looked at how many people around the world were exposed to this open burning emissions. And they predict that on the order of 300,000 to 400,000 people die prematurely each year due to exposure to particles from biomass burning. So it's pretty significant in terms of public health. We took that the 2015 smoke event across Southeast Asia, and again, like more than 70 million people were exposed to unhealthy air. And using short-term exposure, we estimated there was on the order of 10,000 premature deaths due to that acute exposure. There was another paper by a group, Loretta Mickley's group out of Harvard, that simulated the same event, and they actually had a prediction of more than 100,000 premature deaths. So that really highlights, one, the uncertainties in the model, and two, really our how unknown the health outcome dose-response relationships are, and whether you use acute exposure or long-term exposure. But I won't get too hard into that. Just know that smoke has a big negative impact on public health, including increased early mortality. That said, we're doing all these studies, and yet there's a whole host of uncertainties associated with these fires and understanding their emissions and their air quality, from understanding the emissions, their processing, where they go in the air, and then their impacts. And one example here is, so we use satellites to help us identify where and when a fire is burned. We use different satellite products. This is just two different satellite products showing fire counts over two different, during the same day. So if I use one versus the other, I would get very different answers, which is challenging. We can imagine that smoke obscures some of the satellite detections on the surface. When we have clouds, you miss fires. So there's a whole lot of problems using satellite data to help us drive that.
Can you just tell us, what is the satellite? Is it visible light that it's seeing, or is it getting temperature? I mean,
It's getting temperature, so
seeing high temperatures.
yeah.
Red.
Yeah, there's a temperature threshold, and so they do screen for, the near real-time product takes everything hot, and then after they go back and fix it, they get rid of all the flaring and other issues that'll set it off as well.
What is flaring?
Gas flaring from like chemical plants.
Oh,
Yeah. So, but depending on the satellite and the instrument, where it is, when it's over passage, you could miss fires. Another big problem that I have is the land cover, what we use to define what is burning at the surface. And I use global land cover data sets. I actually use the one on the top for my default model. This is called the land cover type. It has, it takes a globe, it takes all the ecosystems in the globe, and assigns one of like 17 land covers. Globe cover, I think, has 22. These are both global satellite products. If I simplify them down to 5 generic categories, which I use in my model: grass, shrub, evergreen forest, temperate forest, and tropical forest, and crops. These are two of the same maps for the same year, simplified to those 5 ecosystems. And you can see I get really different answers depending on what I put in. And for example, in California, that orange is shrubland. If I'm burning shrubland, I have a much lower biomass density to burn, or assumed, than I do if it's forest. Plus I get different emissions. So what I put into the model to drive what ecosystems are burning is really uncertain, and I think something that we need to focus on. So we have uncertainties in emission factors as well. A variation, just so you can imagine how variable a fire is, and if you're going out and flying around an airplane, you can get really different answers depending on where you go. And this is just showing you 2 different inventories for the same period of time. So you can see we have fires in different locations, different magnitude of emissions. It is pretty uncertain. What I do appreciate about this community is that those of us who are doing the fire emissions modeling, we've done a lot of comparisons, we've talked to each other, we have different methods, and I think there is value of having these different methods, and then having those who do field campaigns help us figure out what's right, what's wrong, where we do well, where we don't. This is a paper that just came out in ACPD a couple days ago, I think, or October 24th. And so this is just showing you emissions of black carbon and organic carbon for different years from different inventories. So you can see how variable they are. And this is for boreal North America, the contiguous US, and globally. So maybe globally they align more closely, but as soon as you start breaking out regionally, you can get really different answers. And what's really scary about this is that you put it into a climate model and you start looking at the radiative feedback, or the top of the atmosphere radiative forcing, or radiative effects from the BC on top and the OC on the bottom, you can get really, really different answers just by putting in different inventories. And these are all inventories widely used across the chemistry and climate community. So this was pretty enlightening because you can even get a different sign in your radiative forcing. So to me, this tells us that we really need to do a better job of calculating the emissions and getting them right. And so I think some of the field programs that are going on and have been going on are really going to be helpful for helping us understand this better. We're doing a lot to improve FIN right now, including the way that I'm calculating the burn area for big fires. There has been a wealth of data collected from the chemistry community, including updated emission factors that we're putting in, working with ecosystem scientists to help us better our fuel loading and burning. And then like in Southeast Asia, we're trying to better include peat burning because obviously that is very important. And working and looking at agricultural burning, particularly in the US and in India. Another thing that we're trying to do is better simulate the chemistry. And this is a project that I have funded by NOAA with Kelly Barsanti from Riverside and Amory Carlton from Irvine. And pretty much Kelly and her crew, they go and they measure all the volatile organic compounds in a fire plume or in a fire lab. This is the output from one of their projects that they had. I think she handed me a list of 600 compounds. I have a model that has maybe 15 volatile organic compounds. So how do I take this and adequately represent it to simulate the chemistry as best as possible? And that still is a big question. And I'll tell you, there was a big field campaign last summer called We Can across the western United States where NSF flew around the C-130 and they collected, again, hundreds of compounds. And same thing with this summer with FireXAQ. And the question is, how do we get this to be adequately represented in our quality and climate models? So we can like take all these compounds and simplify them and put them into these classes, these lumped surrogates that we use for models, and look at our old way of doing it, and then based on all these new chemical compounds. And we're finding that this is really, really important. And this is just work that's still kind of ongoing, but we take our assumptions, we take all these new compounds, we allocate all the emissions to these surrogate compounds. And you have to make assumptions. There's some compounds that could fit into like 3. There's some that are not represented at all. So like, do I ignore it or do I put it in and just shove it in somewhere? What do I do? And so we did a whole bunch of simulations. And just the point is, the assumptions I make, and by putting in these new compounds and having really simplified chemical mechanisms, I can get very big differences in our predicted chemical outcomes. And this is just showing you 3 different. This is MPAN, which is a nitrogen compound that reacts and kind of stores nitrogen in the atmosphere. This is terpene oxidation products that can form particles in the air. This is formaldehyde. And the point here is, depending on the assumptions that you make and how well you simulate those organic compounds, you can get really big differences, which are going to have big impacts on the chemistry. So we are working to come up with recommendations. We are coming up with new chemical pathways to include in models if we're going to adequately simulate biomass burning. And we're going to be updating our models based on the data collected this summer and last summer. I wanted to talk briefly about a couple other projects that I'm working on. Biomass burning is not just happening outside, but it's also happening from cooking. And then I'll talk a bit about open waste burning. I got into cooking with biomass from some colleagues at NCAR. And I was fortunate enough to be funded by both NSF and EPA to lead this project called Research on Emissions of Air Quality, Climate, and Cooking Technologies in Northern Ghana, or reacting. This is Ghana, it's in West Africa. The capital is around here in Accra, and our study area is up here in the northeast region, right next to Burkina Faso. It's very hot, it's very dry. People cook with biomass. And so we did a full intervention where we had 200 households. We looked at 2 different cooking technologies, one that we designed in country with people there, and another one was this fancy forced draft stove that needed power and had a fan and was supposed to be the next big thing. And we tested different combinations of the 2 and looked at the emissions. So we measured actually emissions in the field. We measured exposure. So in this picture, the woman is wearing a pack around her waist. It actually is measuring particles. And then the kids, we had CO monitors. We made special t-shirts for those. And we looked at cooking and stove use. We looked at the emissions of other sources as well. What we found is that many of these cook-stove intervention studies that are happening assume that all the exposures are due to cooking. And we found that that is not the case. There are plenty of other sources of particles, even in a rural area like this, that can have impacts on the total PM that people are exposed to. And and that's actually, we have a bunch of papers, and I actually have a whole other talk on this, but I did want to mention this because I think it's fascinating. And one of the things I really like best about this project is that it was truly interdisciplinary. We had engineers, we had health experts, myself, an engineer, and an environmental economist were the 3 PIs. The environmental economist is still there, looking at now willingness to pay and transition of technologies and how that impacts the environment. So it was a really fascinating project. And one of the other things that I noticed when I was there is that there is no waste management, and people burn their trash everywhere. And I went out running the first day I was there in 2011, and I never ran there again. And mostly because people are burning their waste early in the morning when the boundary layer is low and the pollution is horrible. And so I started looking around. I'm like, well, do we include open waste burning in our emission inventories? Because this is obviously a big deal. And I found out that yes, we do include it when it's incinerated properly in a reported incinerator. None of this open burning was included. So I wanted to know how much that was. Oh, and just an aside note, this picture is actually from a US military compound. So this is another thing. In our military compounds, say for example in the Middle East, we have these huge compounds, no waste management. They dig this huge pit the size of a football field, they dump all their trash, they burn it daily, and they have people standing next to it to tend to it. So all these soldiers are coming back with lung issues. They actually just had a lawsuit that made it really far up, and they lost against the federal government. But there is a woman at National Jewish Hospital that has been working with vets coming back from the field and who have had respiratory issues, and they think it's tied to the waste burning that they did. But so I did a paper. Just we have very little data. It's very hard to calculate what's burning where and how much. But what we did find is that the emissions are pretty substantial in many countries, and they are equivalent to sometimes as much as anthropogenic sources. So it's not a source to be ignored. There's been a lot more work since this paper has come out. In fact, there's a new emissions inventory for India showing that open trash burning is huge in India, and it's really important. There's been measurement campaigns around the world, so we're continuing these efforts just to try to understand the impacts. Yeah?
Why do you look at CO?
Oh, this is just one example from the paper. I did all of the emissions. I also did toxics, and I did like furans, and I worked with Brian Goulet, who was my co-author. He's from EPA, and he looks at like dioxins and furans and awful, like really harmful toxic compounds. What's challenging is there's a lot of nasty stuff that's coming out of trash burning. In fact, my colleague Mike Hannigan, we've been burning waste both in Africa and at home, and looking at specific tracers so that when we go out into the field and we measure particles, we can tie back at least some of it to how much is coming from waste burning. But we're just beginning to identify those compounds. What's interesting too is I think like 20, 30 years ago, in many of these places, much of the trash and waste was organic. And then you go now and everything is plastic. I don't know, like where we go in Africa, all the water's in these sachets, these plastic sachets, and people drink them and then throw them in the ground. And plastic is everywhere. So, yeah, I think the waste streams have definitely changed too. And I'm wondering, I'm curious, like how much the emissions from open waste burning have changed over the years. I have no idea how to find out, but just, yeah. And this led me to look at other incomplete combustion sources and wonder like how good are the emission inventories for Africa. I work with Eloise Murray. She's at University of Leicester right now, and looking at all these different, what we started looking at is that the emissions inventories and what we know in Africa is really, really little. And I think they're very uncertain. So we actually did a new inventory trying to capture all these sources that weren't characterized in current inventories. And we came up with an inventory. This is like just an example of volatile organic compounds and black carbon, but we did a whole bunch of different things. Sometimes the VOC and black carbon emissions were the same from all these incomplete combustion sources, were the same order of magnitude as biomass burning for the continent. So it's pretty, they're very important. Again, like highly uncertain. And this is just showing you. So this study is in the black for CO, black carbon, formaldehyde. And these are other inventories that are used for chemical and climate models. These RCPs are what's used for climate modeling looking forward. So you can see that we're totally different sometimes in terms of magnitude, in terms of trajectory. We just looked at 2 years, 2006 and 2013. But there's an obvious need to do a better job understanding these emissions and where they're going. Africa is rapidly changing. It's going to have huge, not only regional, but global impacts as it does change. And unless we even get the baseline right, we're not going to get our future projections right. So Eloise put them into the GeoChem model, and so we looked at the impact on ozone and particle concentrations from these sources. And then Forrest Lacey, who was a postdoc working with me at NCAR, we looked at premature deaths. Again, we took the concentrations coming out of the model, put them into these dose-response relationships, and tried to figure out how many people were exposed and how many premature deaths might be caused by these sources. Again, this is highly uncertain, but I'm hoping that this motivates future research and more work done there. So I have 2 more slides. These are just kind of a sample of the projects that I've been working on. I'm also involved in a project led by Detlef Helmick, looking at fires and fire impacts across the Arctic region. We've been looking at the impacts of peat burning. Like I said, during these El Nino years in Southeast Asia, the fires they burn the peat, they go forever. They emit a ton of emissions. What's awesome about me working in a university now is students come and find me, and I had this one student from anthropology come and find me when I first started a 1.5 years ago, and he's like, I study the largest wild troop of orangutans in Sumatra, and it's in this remote thing, and there was a paper, and he's like, could you look at this paper? And this paper was by a colleague of his who looked at the smoke impacts on the orangutans. And she used 1 point of, her air quality piece was horrible. It was using 1 point concentrations hundreds of kilometers away. And so he's like, can we do something different? I collect the urine of orangutans and I look for metabolic markers of stress. And there are key urine metabolic markers that show stress due to biomass burning. People use this for health studies for humans, looking at cook stove impacts. And so he's like, I have multiple years. And I was like, oh, well, we're doing this peat burning and we're going to be running WRF-Chem for 10 years. So we're going to be doing a health outcome study with orangutans in Borneo. I'm also working on air quality management, like development of strategies and working with organizations and government agencies on the ground in different major metropolitan areas across the globe. This is with an NGO to help them come up with air quality management strategies and also to take advantage of all the stuff that we've already done. We have a wealth of satellite data. We have free model outputs. So there's tools and data available now that can be used that I think that people are still, or places that are still behind us can take advantage of. We're looking at not only like what's going to happen in the future in the Western United States, and then of course I continue to work on emission inventories, India, Asia, Africa. And the other little thing that we've done, and I just wanted to point this out, especially since this paper just got accepted. So one of the things in Colorado is that marijuana recreational use was legalized. It is becoming legalized all over the country. I don't know if any of you have ever smelled a marijuana plant. It's called skunkweed for a reason, because they stink. They obviously emit a ton of volatile organic compounds. No one has been able to study them because they're ruled by federal law and can only measure these plants that are grown in Mississippi in a special compound. So my colleague Will Viswete, he and I went to the same graduate student group, and we graduated from University of Texas from the same advisor. I talked into him into giving us a grad student, Chitsang Wang, and we went and actually did leaf enclosure measurements around plants, measured the emission factors, and then came up with inventories for Colorado. So this is a map. The green dots are the recreational growing or cultivations. The red are the medical marijuana cultivations. And what's unique about Colorado is that the growing operations have to happen indoors. They have to be enclosed and locked. So what's happened is that all the commercial warehouse space, like around Denver, have been rented out for commercial growing operations. And where these all these commercial warehouse spaces are located along the major highway corridors, I-25, I-70. So you have these big VOC sources right next to these sources of nitrogen oxides. And when you have VOCs next to nitrogen oxides, you can get ozone. And in Colorado, it just happens that our ozone is VOC sensitive. So adding a little bit of VOC can change our ozone. And we are non-attainment, so we do not meet the EPA criteria. So we actually came up with an emission inventory. Again, it's highly uncertain, and we put it into the regional air quality model to look at the impacts of ozone from these growing operations. And what we found is it's not insignificant. We've caught the eye of the CO, like our state agency that's in charge of this. Unfortunately, they're still mandated by EPA rules, but Will is now working with groups in California, Canada, and Washington State. So we've made connections again. There's a lot of issues around this whole new economy in terms of environmental impacts and as well as health worker impacts that I think need to be studied. I think there's a lot of opportunity there, and I'm hoping that funding will come, because I think it's a perfect example of how our states get to try new things and test stuff out, but I think there's still a lot that we need to know. For example, in the indoor growing operations, and I've gotten into one, the volatile organic compounds, the concentrations were higher than anything I've ever seen in a petrochemical plant. Tens of ppm, which is very, very, very high. It can lead to toxic events. There's questions whether the hallucinogenic compound, the THC, actually volatilizes, if it can form particle in the air. These are perfect like urban smog chamber studies in these grows. But anyway, there's a lot of questions involved. But we just had 2 papers published on the emissions and the air quality. So I just wanted to highlight that too. And that's all I have for today, but I'm happy to take any questions now, and I'm happy to give you my email address or talk to you or Skype, or I'm here for today and tomorrow, and I'm happy to catch up there too. So thank you very much. I really appreciate it.
Questions to the speaker?
Yes.
I'm kind of curious about satellite, uses of satellite to constrain emissions some
Yeah.
other characteristics of fires. What is the state of that in your opinion?
So I think it's really great, and the newer products, like for example in the U.S. we have the new GOES-R that's helping us with timing and where and when the fires are happening. I think there's still a lot of uncertainty associated with fire detections. I mean, we're impacted by clouds. So anywhere you have clouds, like for example in Southeast Asia, I think we're missing fires. There are burned area products that help us get that burned area, and those have been improving. At the same time, they have a time lag, so those products are coming out slower than when I want to predict emissions for tomorrow, so I can't rely on those burned area products. Yeah, and again, the vegetation, there are improvements with the vegetation, and the smaller the area that you're looking at, I think the better vegetation you can have. There's work being done by the Forest Service that's using LiDAR to look at canopy density and characteristics. And I think that's great for a single fire or for a couple fires in a region. But if you want to do anything global, you're really stuck with the global products that are out there. There is more and more ground truthing of that happening, and I think those products are improving. But I think they're still a long way. But I go back and forth, and I don't know how not to use them or to get around that.
What about things like Moppet or Trumpomede?
So those have been really useful. So Moppet gives you carbon monoxide columns. So I am working with Ben Guibert and CAR, and he's doing data assimilation and inverse modeling of running the model and then comparing it to the CO, and then kind of tweaking the initial inventory to match that. And that has been happening. And then like Donna Hensey has been doing it with ammonia, with Troconi. So there are satellite products that give us chemical composition that we can do inverse modeling to help us constrain where and when our emissions are doing well and where we're totally off. And that's been really helpful. In fact, I just looked at a poster of Davin's grad student a couple weeks ago at an ILEAPS conference, and she had this whole hotspot of I'm missing of the crop emissions. And so I'm trying a different product that's able to see smaller fires in hopes of better capturing the ag burning.
So you're talking about a fire seen before by MODIS.
Yeah.
Right? And that's polar orbiting, right?
That is.
Okay, so
And
you're
then-
basically just seeing like a snapshot
one
of some
day.
area once a day, or
That's right. And then we could use like the GOES product, which gets it every 15 minutes, like in the US we can, or we could use those geostationary to help us get the diurnal profiles better. Because that's the other thing, like with the polar orbiting, we're missing fires, particularly, in the southeast, we're missing all the prescribed burning that happens in the morning.
But I also want to ask, you mentioned your model is producing output with 1 kilometer resolution.
Yeah, so
Is that,
it's
but is it really?
No.
Oh, okay. So you can put out output on 1 kilometer
Yeah.
pixels, but is it really that kind of
Well, I
accuracy,
mean, it's the
or-
resolution of the fire detection.
Oh, okay. That's
So
1
it
kilometer.
is 1 kilometer for MODIS. It's 375 meters.
But that's
for-
that's not continuous.
Yes.
So it's like
No.
the new GOES is about that, right?
Yeah, yeah. In fact, I don't even know because I haven't incorporated it
But
yet.
as GOES-R, is it seen?
Yeah. Oh yeah, it sees fire so awesome. So I'm really excited. I just haven't been able to play with it. But then again, you're just limited to parts of the U.S., right?
In the land
Or-
use data set, like what do you feel is the accuracy, representative accuracy?
I, like that's kind of my high
You
horse
can
right
give me
now.
data
So I'm
on-
like, that's what we need to be working on. Stop measuring all these stupid compounds. No offense
Go out
to
and
these
measure
chemists in the audience,
compounds.
but I'm like, oh, we don't even know what's burning. But I mean, and that's where like products like the FRP is helpful because
What's that?
that's the fire radiative power. So they measure it from space, and that's telling us like the intensity that's burning, and that can somehow maybe help us better give us an idea about how much biomass is burning on the ground. But then again, the NASA model uses FRP, and they still have to come up with some assumption of the type of vegetation that's burning, because they still have to relate it back to these emission factors. And then I work with all these amazing chemists at NOAA who've been in the labs, and they're like, oh, well, we have this temperature profile of emissions over the fire, and at high temperatures we get this, and at low temperatures, and I'm like, no, I don't know what to do with that, because I just want one number for your whole fire of emissions. I don't have temporally varying emissions yet, and I don't think anyone does, but I think that's where we need to go.
You mean over the course of the fire?
Yeah. And then But yeah, and they're like, oh, we'll use satellite. And I'm like, again, that's one snapshot in time of a fire, the temperature of a fire, which changes throughout the course of a day and the course of the fire. So yeah, it's really hard. So yeah, you're never done. But you know, it's one of the reasons why the complexity is so much that I really took a simplistic approach, because I'm not sure adding complexity to the models really adds that much value. It still has these inherent uncertainties to it.
Any other questions?
Yes.
No, Amy?
I mentioned a project on future fire in Western US.
Yeah.
What does that look like?
Oh, not great. So I've been working with Leroy Westerling at UC Merced and Matt Hurteau, who's a fire ecologist at University of New Mexico. And Tony has come up with like future projections, taking all the climate models, and then we try to tie that back to fire activity and fire severity. And in like California, for example, we predicted, I forget what the numbers are. I don't have a slide here either, but much higher, you know, like just it's continuing to get, the emissions are going to be higher. And then Jennifer Balch, who's at the University of Colorado, has been looking a lot at climate drivers of fires across the western United States. And yeah, what's nice is she's come up with some really nice relationships that we can use that'll better simulate the probability of fires in the future. So, but yeah, it's fascinating because air quality managers call me and they're like, well, what do we do? And I'm like, I don't know. I actually, you know, I've been doing some projects looking at like trade-offs between doing prescribed burning versus letting the fires burn, and there are some really good trade-offs, but the magnitude of the forests and the cost associated with land management and doing like the thinning, like they try to, thinning is for like the logging company, when they say thin, like when you actually need to thin a forest for fire management purposes, it's not the same as logging out things that are economically valuable. So it's very costly to do fire management, and yeah, it's an interesting problem politically and management wise, and yeah, and you just look at what's happening in California even today, it's insane. Yeah. But and you all have better climatologists in this room than I am, but I understand that like a lot of the Santa Ana winds and these high, drier, windier time periods are going to happen more and more because of the changing climate. So it's only going to exacerbate the problem moving forward. So.
Well, on that very happy.
Yes, I can say one more. That's funny.
Right ahead.
One per person, like so. About the orangutans. So people ask, like, well, how does he collect the urine of the orangutan?
No, I was going to ask that, but
Yeah, this is the first audience that hasn't asked me that. So he actually goes out at 5 o'clock in the morning, and they know where the nests are of the orangutans, and they go out and they stand underneath them, full rain gear with a bucket. And when the orangutan wakes up, it goes to the bathroom and they collect it, and then they take it all back and do the analysis, the chemical analysis of it. It's crazy. I know that was someone's like master's project. So yeah, I don't know, forget it.
all right, well, let's thank our
Yeah, there you go.